In this video we will add a radio to our Weasel platform that we showed and created in the last video. And this is a platform that will use an MSP430 F5 342, and we want to add a Atmel RF233 low power 2.4 GHz transceiver to the platform itself. This transceiver is brand new, it just came out in spring 2012. And what I have here is a dev kit that's sold by Atmel. So we have here on the right hand side the radio chip. It's hooked up with a lot of different wires, which we will look at later on, to our little dev kit that we had last time. And as you can see, the dev kit itself is actually still running our Blink application that we programmed on it last time. Here on the right hand side I have my good friend Logic Analyzer, and it's actually a Salia Logic 16, a very handy tool for embedded system developers if you want to look at the different protocols and data lines that are going from chip to chip. In this case I hooked up the logic probes to all the different channels so that we can actually sniff and see what's going on within the driver. Now, we don't plan to write a whole new driver. Fortunately, TinyOS does have a driver for the RF230, which is a predecessor of the RF233, and we are hoping to reuse as much of the code as we can. There will probably be some changes since the RF230 had a couple of bugs and mistakes. Hopefully they were fixed in the RF230, and hopefully we can take out these bugs from the code, thus making it more efficient and better. Alright, the first step in adding a radio to the platform is creating the links. As last time with the MSP430, we have to actually copy the right code into the right directories. So here we are in the platform Weasel directory, and let's try to see if another platform is actually using the RF230. So I'll find name RF230. We can see that there's the Mole platform and there's the Iris platform. So let's look into Mole. There's a chips directory in here which has the RF230. So we have a RF230 split control P, we have a radio, HBL RF230P, and a HBL RF230C. So these are all the different configurations that are needed for this particular chip. If you go one back, if you look in the dot platform, two back, if you look in the dot platform file, we can see that the Mole platform uses the RF230 and it actually uses an M16C60 microcontroller, which is different from what we are using. We are using an MSP430. So what other platform was there? There is the Iris. The Iris is another platform which also uses the RF230. Plus, in addition to the RF230, it actually uses an Atmel 1280 and 1 as its microcontroller. So let's base our driver off of this Iris driver. So the first thing we have to do, let's go back into our Weasel directory and we copy over the RF230 directory into our hardware directory. The one thing I want to do, so that we don't confuse it, let's rename this to RF233. And if we go in here, there are a couple of files, and we want to rename all of them to have to be a little bit careful here. So they're renamed, and now we need to rename the files internally. Let's search for 230. I go slowly and don't do a global replace because I also want to take a glance at the files at the same time. This one here should have less changes in it. Alright. This include file we keep for now. These are just configurations, so we keep all of these configurations. and we will have a look at this file in more details later on. Next step, we have to add this directory, so let's edit our platform so that our make can actually find the different files. And directories do we have to add? Well, let's go and have a look at the iris.platform directory. You can see that it has a directory for hardware RF233 that we want to include, plus we want to include the chip itself. Plus it has a couple of more directories, and that we want to add, which is the RFX link directory. So the difference between the RFX link and the chip's RF230 is that the RFX is the higher layer protocol, so this is everything from the MAC and up, including going as far as into routing and other kind of protocols, while the chip's RF230 directory is the low-level driver of the radio itself. So this is what we have to change to adapt it for a 233, and then we can reuse these higher layer protocols that are exactly the same ones for the RF230. And the hardware RF233 is actually just the glue logic that makes this lower level and these higher level layers work together. Okay. Next step, we have to find an application that can actually test all of this code. So I have here one prepared. This is in the apps test RFX link test transmitter. So this is a test application that tests the transmitter to make sure that the driver doesn't lock up while it's receiving something, even though we try to force and actually try to send something out. Trying to build this for the Weasel platform will show us there's a lot of mistakes still that we need to start fixing before we even can think of compiling this properly. So what do we have? Make it more clear of where the break is between these different codes. So the first problem is that we don't have a platform message H. That's easily fixed. We can grab this from the Iris platform. I'm sorry. Here we just make sure that everything is in here. This is just header definition for the radio messages. Let's see more files. Asks for a mica timer. Okay, so now we have to start digging a little bit deeper into these RF233 drivers. The first one is the configuration. Since the Iris platform is actually inheriting a lot of things from the older mica platforms, because they all share the same microcontroller, we now have a completely different microcontroller. So we don't use the mica timer, we just use a timer directory. We keep these values for now. These are just default values that we might rename later on to RF233, but for now this is fine. We have here a function that defines how to calculate the CRC. The old RF230 chips did not have a function for a CRC. So what they did is they used the CRC byte command in order to check for the CRC. This will be one part that we will have to change because the newer chips can check the CRC directly on the fly, so we will have to add code in the driver to make sure that we don't actually calculate on the microcontroller, but use the peripherals that the radio chip itself actually provides. So right now, CRC CCITT update is actually a function written for the Atmel chip. What we can try to do is actually look at the Mole platform to see how they redefine this. Let's go over into Mole chips RF230 radio config. So what they do is they actually added in a whole function that calculates the CRC. Why don't we just copy this right over? Because this is the manual calculation instead of using a precompiled version, and that way we can actually remove this CRC16 library itself. We will replace this later. So what we can do here is another fix me use 5233 CRC checking instead. But for now, this will do. We then have the radio itself. So they defined a T micro as the T radio, and here we have T1 as T radio. I agree. We switch this over to T micro 2. This is basically the type of that the radio will use. How many ticks do we have per microsecond? This is all definition for the platform-specific device. This is currently not defined, so why don't we just say that this is let me just do the radio on microsecond. I'm sorry for this misshape that happened. I don't know exactly why the recorder crashed. Just to make sure that you get all the changes, you can go to the link that you saw just before, and you will get to this website where you can see all the different changes that we checked in, all the files. Many of them are just copies of the RF230 driver with some slight modification, renaming from 230 to 233, and we will later on actually start editing this to make sure everything works. Alright, so the next part where we actually stopped was the following stage. So if we are here in the directory of the test application, if we take make weasel, what we get is only one error. There's no match in HBL RF233C at a specific line, and if we go and jump to that particular line, we can see that this is actually the fast SPI interface. So what is this fast SPI interface? Fast SPI interface is an interface that the RF230 driver introduced, and more concretely it was Miklos who was thinking that, well, we can actually optimize this regular SPI interface quite a bit. SPI is a bidirectional full duplex system, so when you write something to the SPI bus, you always receive a byte from it. And the fast SPI interface takes advantage of this particular system. So if we go and search for fast SPI NC, which is the file that introduces this interface, we don't find it. Let's see, did I misspell it? Yes, fast SPI byte. Alright, it's in interfaces fast SPI byte. We can see that it has a split write, a split read, split read write, and the write command. So implementing this should be fairly easy. It should go in chips MSP430 fast SPI byte. If you look in here, you can actually see that the USART of the old MSP430 has this fast SPI interface. So let's try to implement this also for the fast SPI in the X5XXX drivers. If you go here to X5XX USCI, you can see there's a lot of different components in here. And what we want to do is dig a little bit deeper in how this all works. So there's a generate. Let's see what this does. The implements equivalent for different modules, which is actually really nice. So all we have to do is edit the B0, A0 and B0, and the rest will be generated for us. First, let's go and have a look in MSPUSC or SplitRight. So that's in MSP430 SpyP. It has the SpyByte implementation that it provides. SpyByte. This is the underlying implementation, and all the others, I assume, just implement the actual system. So, SpyP0C. Do is SpyB0P. So what we can see is that all of these are just pass forwards for most of the implementation, generating a new component and instantiating it, initializing it with the right interrupt and to the right pointers. So on the left hand side we have the main interface. So this is where we want to add our interface fast SpyByte. All we want to do is say that our fast SpyByte is equal to SpyC fast SpyByte. And here we want to say that export fast SpyByte, and all we do again is say that this fast SpyByte is nothing else than SpyC. Let's fix some of the alignments here. And now we have to go and open MSP430 USCI SpyP. Just the actual implementation. Yet again, this interface provides fast SpyByte. The only thing that I wonder is, alright, no, I think this is it. I still wonder a little bit where you make the link between these I/O lines and which actual GPIO lines they go to. Let me quickly go back into. Now this one we want to stay here. This is where we have to modify everything. SpyA0. C. It's directly the interface. 0P uses these. Well, we will see, I guess. So now that we have the fast SPI interface, we can go back here. We can look in the USArt implementation where we saw them before. If we go here into the SPI no DMA 0P fast SPI, which uses the generic interface here, fast SPI byte. It's not implement, it can be. So it provides this interface, but it doesn't do anything with it. That's strange. Let's go and look again. If we go one back, two back, fast SPI pipe, we can find them in here. So you see in SPI.c, in SPI no DMA P is where they are implemented. For 30 SPI. Where is it? Oh, we're in the wrong directory, that's why. MS-30 USArt no DMA P. No DMA P. Here we go. Alright. These are the implementations, and I assume we can make very similar implementation on the other side. Look at the SPI byte, right? These interfaces are almost identical. So all we want to do is SplitRight, SplitRead. Want all these interfaces here. So the SplitRight has to probably change a little bit. This is a write, SplitRight. All right, I think. Let's see if there's anything else. Nope, this is it. So close this and let's go and have a look. So the first one is the SplitRight, and all it does is basically it transmits. So what we want to do is find here the transmit and command and see how this actually transmits. So we have a packet send, and what we actually want to have is the SPI byte interface. Transmit something. We don't want to do the receiver itself. The way they do this is by waiting . Maybe this is not as easy as I thought. So this here just initializes a transfer. So what we want to do is transfer buffer. This is okay. This is it. Alright, this is it. Instead of just doing a transmit, what we want to do is we are waiting and for the transmitter to be ready, and then we write something out. But we don't actually read. Because the next one is what we do is in a split read is actually exactly what happens here. That's the second part. We read so we wait for the interrupt to happen. If the interrupt happens, what we do is we get the status, we get the buffer, and then we return that buffer. And if there was a mistake or error, we return that one too. Then the split read write is basically just the same thing as before, just first a read and then a write. What we do here is first a write and then a read. So what we want to do here is this. We first want to read. And then we transmit the data out. So we first read. Instead of using data, we use B. So read. Now we have to do a write. So why don't we interesting. Okay. Instead of doing it this way, we can do is call fasts by split read. And then we do call fasts by split write. So we first read, and then we write back, and we return what we read. That should be right. And then the last one is a by write, which is basically the last command. So what we do here is they do first a split write, and then a split read. The other one is first a split read, then a split write. Alright. I think this is it. This should be the whole magic. And if we generate it listing, okay. It modified all the SPI components. So let's see what happens if we do a make equal. Stat is undefined. Alright, that's not too bad. That's actually pretty good. So it's this stat here that didn't get found. So let's look at P. Oh, this was from a different file. Okay, this is it. I forgot to copy this variable here. And this one here, we have to add it. And what else? 183, we don't have data either. That's easy fixed. And it still can't find fast by byte. Alright, let's see. MSP for the USCI SPY A0C fast by byte. So I couldn't find it in SPY A0P. MSP for 30 USCI SPY A0P. And it also isn't here. So SPY B0P should actually have these modifications. Oh, that's the wrong one. SPY Z0P. Ah, this one does not have it. Fast SPY byte. For some reason I thought I made these modifications. Let's see if it worked this time. Ah, there we go. And this is exactly one thing that I was still missing. I didn't know how the SPY component was set up to get the CMOS, SOMI, and all the different connections. So now we have to configure those and hook them up to the right pins. How do we do that? Well, as always, we go and look how other platforms did it. Let's clean up a little bit. If you go into platforms, let's look at the MM5S. USCI. Platform USCI map. This is where they configure the pins. So let's go into our own platform. USCI map. So we have the UART, we have the SPY connected. What we want is we have another SPY, and that's SPY A0, because I think that's where A0P is connected. A0C, mostly because we actually had this configured as a UART, so let's uncomment this. 0, so meaning clock should be configured now. But now, of course, the UART is not very happy. In the platform serial, where the problem is that we don't actually have a serial port. Except I could hook it up to UCA1. Or UCB1. All that it matters. So let's do that. We have UCA. Let me check. Mode C is actually on 22 and 23. That's UCB0. So we are using UCB0 as a spy. So I think I made a mistake in getting the spy unit configured. Yeah, we can just use this whole other platform, UCB, and we should be just fine. So we use UCB0. So instead of this, we use UCB0. And it worked. Isn't that great? So we now can, our driver should start working as soon as we start executing and programming this image. And we can start looking at what the driver actually does and see if this radio is code compatible with what we had before. Okay, so next step would be to program our board, and then we want to look at the SPY interface to see what's actually going on. So as last time, we just compiled the whole binary, and then we do an MSP debug, RF 500 program, and the binary is in build weasel main exa. So it found it, it's programming it, and we can see that it's 10K large, which is a rather big size, I would say, for a binary on an MSP, so it will take a little while. So we're almost there. And done. Alright, so all LEDs are on. I have no idea if this is good or bad. So right now let's start our logic analyzer and Oh, we can't see anything, which probably isn't great. Let's collect a little more samples than just the 1 mega samples. Even with this setting, there is nothing at all. So what we can do is let's trigger on the MOSI and see what happens if we send a reset. Question how to do it. Reset. There we go. And well, there is nothing happening. So that's a bummer, but I guess we now have to debug this whole system. In order to do that, I'm not going to use what we used last time, Eclipse, because I'm not the biggest fan of Eclipse. But what we can do is we can do a make debug weasel. Program it. And then we are going to use plain MSP debug to actually go and see what's going on. In the meantime, let's find out why MSP debug is so slow. Almost there. No solution for MSP debug, so let's just wait on that one for a little longer. And we're almost done. Next, launch this with the GDB. And we are there. Let's set up target. Target remote. Break at main. And let's go. Alright. Actually, this is not really the GDB that I wanted. I want to do the GUI interface where you actually see the source code, which is really neat. So again, target remote. Oh, that target probably died. There we go. No sources available. That's weird. Let's try this again. There we go. Alright, we step over the atomic. Not too interested in the scheduler either. Platform init. Let's step into that one and see what's actually going on in there. So here we are creating inputs. Here the clock. And what the behavior you can see here is fairly simple. It jumps all over the place because we optimize the code a lot. So in order to debug this a little bit easier, let's change the target from make. Let's see what targets we are actually having available. They are in support, make SP430. You can see here the debug optimized, debug no optimized. So if we do a debug opt, it just adds the -G to it. If we do the debug target only, it does the -G and it doesn't inline it. And then the no opt changes it to 0. So -0 is really not very useful at all. So that just adds way too much. So let's do a -01 and make weasel debug no opt. And then we can, oops, that's the wrong command. Let's install this. So increase it by 3 kilobytes. So that's a significant increase. 30% more, almost 40. But it will be very useful for the debugging step itself. So we have some time to see if we can speed up the programming itself. Fortunately, nothing at all. So we're almost at 12K. See if the Celia logic is still going hard, so nothing triggered. It could be that I'm just on the wrong SPI port, but let's first see what's going on. Check it out. So I will keep debugging this, and once I found something, I will get back to you.